guys, let's finish up the elimination handout. I think we're right here. Is that right? Use of a polar solvent. To do what? Number 2 is under what? Use of a polar solvent to...
Clever ways to make the ionization of an alkyl halide.
Okay, ionization, yeah. Getting leaving group to leave. Sounds like SN1E1. How can you get the leaving group to leave? What's the role of solvent? Well, if you want to make ions, what type of solvent do you want? Polar or non-polar? Polar. Polar solvents are going to support ions better. It's going to lead to faster ionization. You put HCl in water, what does it do? It ionizes, make H3O plus Cl minus. You put HCl in hexane, what does it do? It don't ionize. Because hexane don't like ions, and so it just likes, and it don't. So, polar solvent will encourage ionization. So there's 2 reactions shown here. We can take this alkyl halide benzyl alcohol, carbon with the leaving group, the oxygen potential nucleophile. Is it weak or strong? See, I already just gave it away, but if you were just looking at these 2, which one has the leaving group in this reaction? Why is the OH not the leaving group? Well, is there any acid included in this reaction? No. I don't see any acid, so OH can't be a leaving group. So Br must be the leaving group. Do you see any other leaving groups up there? Which one? The H?
I'm looking at the products, so we have to have an H.
Well, the H has left the oxygen, but it's not called a leaving group in terms of, it's not taking electrons with it in terms of, the H is removed by an acid-base reaction. It's not taking electrons with it as a leaving group does. If you look back at the very general intro to a leaving group. You do this with a polar non-nucleophilic solvent. Why do you want the solvent to be non-nucleophilic?
So it won't react.
So it won't react. I mean, some solvents like ethanol, would you want to use ethanol for that? No, ethanol would have another OH and it could react. So that's what that terminology means. What are example solvents?
Dimethyl salt oxide.
Thank you. Do you have the handout from like week 1 where there was a page that has some solvents in there and they're divided by water soluble and not? Okay, if you look on there, you'll see nitrile and DMSO most likely. These are called polar aprotic solvents. Aprotic meaning it doesn't have a proton such as ethanol. We get that reaction. What's this mechanism? Obviously it's a substitution. That oxygen, with that tagged onto it, has replaced the bromine. So it's an SN1 or 2? SN1, yeah. Okay. Plus HBr. Down below, if we do it in a nonpolar solvent such as hexane, I bet you Five Guys hamburger that it ain't gonna react. Or tofu burger. Because the hexane is not going to facilitate or have this, it's not going to support this process here, which has an activation energy. This cation, we haven't talked about it, but ions typically need to be solvated. They need to be hugged by solvents and stuff. These polar solvents will sort of hug it and allow it to form. Hexane is not going to like that guy. And so you can get into the physical chemistry of it, of why and everything that's sort of beyond this, but it's just not going to occur. Probably it's just the simplest way for us to say it is the transition state energy is just going to be too high. There's no stabilization of the transition state by hexane. Again, we haven't really looked at that, but I hope you get the point. A polar solvent is going to be better for a polar process. Okay. Let's move on to a different topic. Deuterium isotope effect. This is a very important effect, both specifically what we're going to look at, but it's seen in lots of various things. I even include, I think, on the back page an example of where this is used in drug discovery. And some drugs these days are actually including deuterium in there. And so the question becomes, well, why? Why deuterium? First off, what is deuterium? Isotope of hydrogen, where the atom has one more what? Well, it's not one more. It has a neutron, because regular H doesn't have a neutron. So it's an isotope of hydrogen. You can call it H2, but we don't call it H2. Instead, we call it D, deuterium. Okay? Now, its chemistry is pretty much similar, same. Okay? It has some differences. For example, a C-D bond is stronger than a C regular H bond. So C-D bond is stronger. That has to do with just sort of the mass effect. Okay, this is a neat way to determine if an elimination reaction is E1 or E2. Look at this reaction. If we take this, heat it in pyridine, without the nitrogen, it's benzene. With the nitrogen in the ring, and there's a long pair there, of course, that's called pyridine. Pyridine is an sp2 lone pair. Is it a strong base or not? Well, I call it sp3 nitrogen strong. What about sp2? It's kind of borderline. So how confident are you going to be saying, hey, it's strong, I know this is E2? Maybe it's not strong enough and it's actually going to be E1. Well, how could you tell? Deuterium isotope effect. Let's see. First off, forget about deuterium isotope effect. Tell me a way you already know to tell this. Tell me a way you already know. What's your rate equation? If it's E1, which one is involved in the rate equation? If it's E1, this is only involved. So if it's E1, you can change the concentration of your base and it won't matter. What if you change the concentration of the base? What if you double the concentration of the base and the rate doubles? Sounds like it was involved and thus it's E2. So you could do just a rate study. Another way is to, that was number one there. Another way is to do a deuterium isotope effect study. And here's what you do. You do the reaction, you get a rate. Then you repeat the reaction with a substrate that has a beta D instead of a beta hydrogen. So what H are we talking about? Which H is the one that's being removed? Right there? Yeah. So there's an H there. But instead, let's do it with a D. Now you would have to make that starting material. Deuterium compounds can be made. Now, before you read on, let me ask you this. Which mechanism, E1 or E2, is the beta hydrogen abstracted in the rate determining step? What rate determining step of E1? Forming carbocation. That's it. Then you remove the H in a fast step. What about E2? Is the H removed in the rate determining step?
Yes.
Yes, and E2 is all concerted. You remove the H, neutrons move in, leaving group gets kicked off. So only in E2 is the H removed in the rate determining step. Now a C-D bond is stronger. That means it's more difficult to remove. And the transition state of removing it is going to be higher in energy. Now if we replace it with D, let's say we replace it with D, and then we do it, and the rate gets slower. Which mechanism thus is operating? U2. It would only get slower if this bond is broken in the rate determining step. And only in E2 is that bond broken in the rate determining step. If you put a D on there and the rate remains the same, that means it's more likely E1. Which, if it's E1, what's the rate determining step? Same as an S anymore. That's your rate determining step for E1. Did we break the CD bond in that rate determining step? No. So having a D there shouldn't influence the rate. So you do the experiment, you repeat it with a D and see if the rate changes with D. If it does, it's E2. It means it's being broken in the rate determining step. A CD bond is about 7 times stronger than a CH bond. That's what it says here. Do we understand that? I was just sort of saying it. It's rewritten right there. Does that make sense what I said? Question?
So in the case of drug design, I know there's a third isotope of hydrogen that has 2 neutrons.
And that's what's called tritium.
So why don't they use that instead?
Well, what do we know about tritium?
Radioactive.
Radioactive. I don't know if that, I don't know the chemistry of tritium. I know they do tritium-matic in SRS. I've never seen any drugs with tritium, but you know, something where you need radioactivity. I don't know the medicinal chemistry of tritium. In terms of deuterium, though, why would a drug company want to put a deuterium in their drug? Before we look on the back page, somebody look. Somebody give me a what?
Longer half-life.
How did you know that?
It's stronger. The rate is slower. Yeah, it's safe.
You didn't look on the back page, did you? Okay. Let's look on the back page and explain it. Comment? Did we finish that up? We can come back. I think it's on the back page. Or a page over. I'm not sure what type of drug this is. Oh, it's an HIV drug. It's metabolized. Here's how it's metabolized. Right here, there's an H, and the body oxidizes this carbon and slips in an oxygen. That's very common. It's often called para-hydroxylation. You end up with an O here. But to do this, the CH bond has to be broken because it's gone. Become the CO bond. And apparently, when it gets metabolized to the OH, the drug is no longer active. So okay. Well, if you want to extend the half-life, make the drug last longer in the body, you like to keep that from happening. How can you keep this from happening? What if we replace this with a D? It's going to make the bond stronger. And that's, we're not doing SN1 or SN2 here, but making that bond stronger makes it more difficult for the body to metabolize it in that manner and deactivate the drug. Stronger bond strength, slower metabolism. In this case, metabolism, you don't want it. In other cases, you may want the metabolism. So is that a reasonable application? Does that make sense? Let's see what we finish up over here. I think we already pretty much did that. If not, let me know. Let's move to this page here. Products for these reactions. somebody have a product for the first one? Somebody ever have a product? Hopefully you worked on these already. You got something? Why did you say plus an enantiomer? It looks like you showed a racemic product. You showed one and then you said plus an enantiomer. That means racemic, right? So what was your mechanism for your substitution? This asks for both substitution and elimination. Substitution, you did what type of reaction? SN1 or 2? Why did you do SN1? What's the nucleophile here? KOH. I mean, that's weak, but you got a strong nucleophile. This is just solvent. Strong nucleophile is going to be SN2. Strong nucleophiles are bullies. They stick their nose in their backside. And they, here I come. And so instead of racemic, you're going to replace the bromine with the OH and you're going to get what?
Inversion.
You're going to get inversion. Looks like it should be SN2. Right? So the SN2, I'm going to draw it down here. I get something that writes today. D is there, and this is going to be SN2 product. Does that look right? SN2? Okay, so what is going to be the elimination product? It's going to be E1 or E2?
E2.
E2, it's the same thing. It's a strong base. It's going to be E2. So what's the E2 product going to be? Ah, we have a stereochemical requirement. Somebody have an E2 product? There's a deuterium down there, but I mean it's beta. There's also an H here. And there's also H there and H here. A, B, C, and D. Look at that.
Do you consider deuterium another substituent?
No, deuterium is an H with just a D on its back. But we do know it has a stronger bond, which is a carbon.
So it's more than likely not going to do that one. It's not going to create the double bond. Or the B2.
Well, first off, what of the four there, which ones meet the stereochemical requirement? HB or the D?
Yes.
Because they're trans, and thus will also be anticoplanar when you draw it in a chair conformation. Things that are cis are not going to be anticoplanar or transcoplanar. So, you're either going to remove this H in the BR or the D in the BR. Now let's look at the products. If you put double bond up here, is it going to be mono, di, tri? What's it going to be?
Die.
Di-substituted. If you put it down here, it's going to be what? Also di-substituted. So either way you go, get di-substituted.
So you're going to go with
Really, that probably doesn't matter. We don't want to start comparing apples and oranges. Which is going to be easier to do? We're doing a concerted elimination. Is this going to be easier? Or is this going to be easier? I think taking that is easier because that's a weaker bond. It's going to be easier to break in that transition state. The product here I would show is going to be double bond there. The D remains here. And which H remains here? A. that is a di-substituted. It's got 2 carbons. I mean, that's an H, that's an H. That's just illustrating that the weaker CH bond is going to be broken.
That's actually the possibility of the other one being because it has enough heat to take the D off of
Well, not as a major product. I mean, one's going to be like this. Well, you're really just going like this. The other one's going to be like this. Starting material product. Breaking the CD bond is going to have a higher transition state because it's a stronger bond. That leads to a higher transition state of breaking it. Okay. I don't know if we got the question answered, but there may be others in the workbook. It's a combination of knowing the stereochemical requirement, and then that leads us to, you got 2 choices. And thus, we had to say, well, how are we going to decide if you got 2 choices? Well, I went with the weaker bond, weak broken. How about down here? We're still showing both substitution and elimination. What type of mechanism substitution are we doing down here? SN1 or 2? I see ethanol, that's a weak base / nucleophile, it's also a solvent. It's weak. It's silver nitrate. What would that be used for?
Is the chlorine a better one to get the chlorine?
What does silver do?
Make chlorine a better.
Promote ionization of the chlorine. So what does this mechanism look like? Looks to me like carbocation chemistry, and if you're doing substitution, that's SN1. I mean, the first step is going to be this ionizing, but we can sort of show it complexing with the silver. I sort of showed it a little bit. We can get to not there. I'm not going to do full mechanism. Hopefully you get to that point. So what's the final product? What's going to happen at this point? I heard it. I think we're going to do hydride shift. Go from secondary to secondary but resonance, because that's benzylic resonance stabilized. Anytime you do a hydride shift, I would recommend doing that if it goes to a better cation. Then the ethanol attacks here. After you lose the H, what do you get? Oh, ethyl. I could put ET, or I could put the ethyl there. And that's going to be racemic. Not doing full mechanism. We've done these mechanisms.
So why
Well, it certainly could, but we sort of said in here that anytime you can do a rearrangement of carbocation to a better, I suggested just doing that in terms of saying, what are we going to predict as major product? So we end up with that ether over there. I'll eventually find a good marker here. So I say that's the SN1 product, racemic. What's going to be the elimination product? E1? Okay, what do you get with E1? Zaitsev. So what's the product? Where does that come from? It comes from the same cation. We just eliminate a hydrogen. What takes the H? By the way, back over here with the Br, what's the Br with now? That's silver bromide. That's going to precipitate out of solution, very insoluble. Mechanistically, what would you show taking an H? You could show ethanol taking it, or what else could you show taking it? You could show nitrate taking it. I mean, we can draw all that out. I'm not going to draw it out. You could show nitrate taking it. Either one, I'll take that one so I can move these electrons in. And we would get to that. And you could show nitric acid as a byproduct. If you want a sort of a neutral byproduct. Or ethanol could take it. You could show ethanol protonated in NO3- as a salt product. Question?
So those hydrogens aren't beta hydrogens, right? Like, because they came off the same carbon as the chlorine.
They're not originally a beta hydrogen,
So it's not.
but they're beta compared to where the carbocation is, as if the bromine came off there. From the rearrangement, we got a little. At this point, it's almost like the bromine used to be there. I see what you're saying. We're actually losing, and I don't know how it got to become bromine with the chlorine. I see what you're saying. We actually see one of these H's moves over here, and you actually lose one to put the double bond in because there's no H over here, right?
So it's still beta because you essentially shifted one from the beta carbon.
Yeah, it's just not. But I see what you mean. It is not beta to the original leaving group with the rearrangement. Okay, did those look pretty straightforward? Last topic here. Double E2 elimination. No, it's not a new James Bond movie. That's called Spectre, Goldfinger. Double E2 is a way to make alkynes. You're doing it in the lab this week. Let's look at this. You've got two leaving groups. They can either be vicinal, that is next door to each other. They're in the same vicinity. What vicinal means. Or they can be geminal. Geminal means they're twins. Geminal, they're on the same carbon. Okay? Let's do this one down here first. Benzene green, there's no beta hydrogen there. We draw it out, there's no beta hydrogen, but we got two beta hydrogens here. If you react this with two equivalents of a strong base, you can do a double E2 elimination. Hydroxide takes an H, electrons move in, you kick off the leaving group. Now the H and the leaving group you're kicking off here have to be anticoplanar. But if you've got two H's, it really doesn't matter, because one can be. There's also no stereochemistry here, so this is not quite like the one you're doing in the lab, which has stereochemistry. If you do this elimination, you're going to get, actually, what do you get first? And it's going to have one bromine, one phenyl, and one H remaining. Now, this is most likely going to also be this has potential for also being the other stereoisomer, because this alkene here is what? This looks like Z. You can also get E. Pretty sure you're going to get both there because there's no reason to only get one here. Now, you can eliminate again. Second equivalent of hydroxide. Take the H. These electrons move in, pick off the bromine. And what does that give? Now we have triple bond with a phenyl on the end and a ethyl on the other end. These two carbons are now linear, and we just made an alkyne by doing a double E2 elimination of the geminal dihalide, and I'm hoping for the question.
Sorry. But wouldn't that be Z for the alkene?
Isn't this Z?
Yeah, but it is.
That's Z.
It's plus Z.
I said plus Z.
okay.
Yeah, plus the other one. Now, by the way, the anticoplanar is still here. What's the relationship between the H and the bromine here? Trans or anti, kind of synonymous. They're also coplanar. The E, they would not be anticoplanar. They'd be syncoplanar. Syncoplanar actually can also work, but it's just never preferred over anti. Question? Do what? Oh, you can do E2 on tertiary halide. You just can't do S into it. And that's not strictly tertiary because that carbon is not strictly bonded to three other carbons. But I know what you mean. I'm still waiting for the question of why did you do that? Question?
Why did you?
Well, I want to know that. E2 on the what? Oh, tell me more. What are you referring to? This bromine's not on a tetrahedral carbon. Right? It's not. This is the first leaving group we've kicked off of a non-tetrahedral carbon. Yes, leaving groups can leave non-tetrahedral carbons. Problem is, don't ever do it unless when you're doing double E2. See, lots of things can happen, guys. But if I tell you everything can happen, then you'll do everything and you won't know what can happen. So I've told you, hey, tetrahedral carbons. But you're right. The second leaving halide is leaving from a sp2 carbon. That's one reason this takes a lot of heat. And it can be a little bit difficult why you had to heat for 30 minutes in a higher temperature in lab than normal. But you're right. The leaving group is leaving an sp2 carbon. Just be careful when you do this. Now up there it's a bisphenol. That doesn't matter. From that carbon, here's a beta hydrogen. From that carbon, there's a beta hydrogen. You can just remove HCl and remove HCl. You can do it twice, it just they're not on the same carbon. So show the product up there. There I use just another base, a sterically hindered one. It doesn't really matter. And you may want to show the intermediate, you may be asked to show it, but it'd probably be the same thing. probably a mixture of E and Z. Just show the final product. Final product is going to be what functional group? It'll be an alkyne. So what's it going to look like? Be that there. I drew it sort of straight up and down, but you're going to have a T-butyl group, and you have a carbon triple bonded to a carbon. All right, we're going to put in a double bond when we remove one, then we'll put in another double bond, remove the other. That becomes triple bond. That carbon is now linear, right? That's why I drew it linear. There's two H's here. One there, we remove HCl and HCl. The last carbon has an H remaining. Carbon's got an H there, right? I mean, it's only carbon is a terminal alkyne. Hopefully you see that. That can be done. That'd be double E2 on a vicinal dihalide. By the way, how do you make vicinal dihalides? How would you make that compound from reaction we've done in this class? Actually make it from the alkene. And what would you react it with? Cl2. Final exam is coming soon. If we wanted to create a never-ending circle here, how would you convert this back to this? Anybody? H2 and Lindlar's catalyst? Yeah? You can actually also do a dissolving metal reduction because there's no stereochemistry here. Yeah. Et cetera, et cetera. Oh, very bottom. We did start with one step of that. What's a one-step synthesis of that? You may not think of it as one step, but like one reaction, one flask. So this is the only way to make this that I know that we have done is to actually start with the triple bond. This and react it with what to get that? HBr, how many equivalents? 2 equivalents. That's actually the reverse of what we did. This removes 2 HBr by double E2 elimination. If you want to get back, you add HBr, but we did that reaction. You know, double addition of HX to alkynes. Now these are going to be on the same carbon because of resonance. Okay, I think that's it there. I think that finishes up with elimination. Any questions about elimination? Let's look at the very first page again. Now that we've done this, what was the example of elimination? They've got this compound with the iodine. They reacted with DBU. DBU is a neutral nitrogen base, but it's fairly darn strong. It's actually stronger than a tertiary amine or a sp3 amine. It's a strong neutral amine base, strong enough to do E2. They just eliminate. We got 2 H's there, they just eliminate here. I mean, there's also an H here. Look at this. The H there is the astrobold. It's bold with S dash. Are you going to eliminate that HI?
No.
No, they're not trans. And so they would never be able to be transcoplanar. It makes sense that the other H was what was eliminated, right?
Yeah.
THF is just a common solvent. It's an ether solvent, boils about 60 degrees, 12 hours. They probably, DB is a fairly weak base, it's strong enough to do E2. Probably because of these other functional groups, they couldn't use a stronger base. If you had used hydroxide, you would have done something over there. So that's substitution and elimination. And in the 1 minute we have left, let's cover UV vis. We will do that. UV vis we'll cover on Tuesday, and then we're off, and then the test the following Tuesday. Okay. This Tuesday we'll also see if there's any questions to answer. Hopefully you bring questions. Please look at the UV vis handout, including the picture of the carrot. Any last things, guys? Some of you have lab tonight, right? Double E2. Okay, guys.